We have Charles' law that says the volume of a fixed mass of a gas. Fixed means we can't change it. So, do you guys see why this gas is fixed in here? Right? It's fixed because I'm not letting any air in and out. It's sealed. The balloon seals it. So all I have that's in there is that air. It's in there. Okay? The pressure's fixed too because the outside pressure is the same as the inside pressure. Okay? So the outside pressure is the same as the inside pressure. If it was different, then that would mess our law up. The volume is changing due to the temperature changing. And the temperature has to be Kelvin temperature. Okay? The temperature has to be a Kelvin temperature. So, anybody do a lab where when they did their lab, they were directly related. They had a direct proportion, had a linear line. You guys did?
Yeah.
Okay. Who else did? Anybody else do one that was directly related? We only had one group do the temperature. Did we have another group do temperature and pressure? You guys did, right? And yours was directly related as well. Okay, by doing this, how did you guys figure your constant? Did you multiply the variables or did you divide the variables when you tried to find your constants? You remember? Do you take P, in this case you would take, do you take P or V times T to get a constant, or will you take V divided by T? If they're directly proportional, what's it say that you need to do to find a constant? Is that in your notes? What's it say about directly proportional that what you have to do? You divide. Okay, so let's do that. Let's take our V and divide by T. And that will give us a constant. So we can take V divided by T, and that gives us a constant. You can do that at all different types of volume and all different types of temperature. Okay, so we're going to call that V1. We're going to say V1 is a particular trial, like you guys did different trials. And we'll go T1's a different trial, and that equals K1. K is just a constant. All right, that's all it is. And constant means that value is going to stay the same no matter what you change the temperature to. The volume will change with it, and then by taking the V over T, you get a constant. So then we'll also take V2 over T2, and we'll get a constant too. We'll get the second constant. How does K1 and K2 compare? What do you think? What's their values going to be like? You may want to guess. Yeah. They're going to be the same. Since it's a constant. Like when you guys would, if you guys ever would take the circumference of a circle and kind of work backwards to find pi, is it always 3.14? Right? Okay, so this would be the same thing. Okay. So what we can do, we can set up a scenario. We're going to set up this scenario with this container up here. I'm going to make up some of the numbers, but you can kind of see what's happening along the way. Okay? I'm going to go ahead and do this setup. So we're going to take V1 over T1, and we can set it equal to V2 over T2 because the constants are the same. So this is Charles' law, and this is what you would do to solve for Charles' law. Okay, so we're going to take this flask here. We're going to cool it off a little bit. So I'm going to get me a container where I can cool it down a little bit. And we'll say that this temperature of this water is about room temperature, which is 20 degrees Celsius. So we're going to get this down to about 20 degrees Celsius. It's going to kind of suck in a little bit. Probably won't go in the whole way, but it'll suck in a little bit. So as we do the experiment, the volume of the gas is getting bigger. I'm not saying it's probably, we'll let it get a little bit bigger and then we'll make a kind of a guesstimate of what the volume is. So the volume has went from the size of the flask basically to now the flask plus the balloon. Okay? So we're going to say it went up 2.5 times in volume. We're going to say the volume is actually 2.5 times its original volume. So if that's the case, we're going to take that and make about 2.5 times that size. So that would be 260, 360, no, what would be that? 325? Yep, 325 is correct, thank you. So it'll be 325 milliliters. We're going to solve for T2. Now, according to our definition, are all our units correct? By looking at the definition of Charles' law, all our units correct? Read through it again, look at my units, see if they're all correct.
No.
Okay, so what do I need to do? Yep, I got to change Celsius to Kelvin, right? So every law that you do, you have to have Celsius in the Kelvin. And the most common mistakes why students miss problems on quizzes and tests, they leave this as 20 degrees. Can't leave it as 20 degrees. Because if that's the case, if I heat it up to 40 degrees and it doubles in temperature, then the volume would double, and that's not the case. That doesn't happen. So let's change this into Kelvin. So what would it be in Kelvin? What do we have to add to 220? 273, so it'd be what? 293 Kelvin. Milliliters does measure volume, so I'm okay with that. That's fine to have it in that term. Now, I want to solve for T2. One of the best ways to do this is just to cross multiply the symbols to begin with. So if I cross multiply the symbols, then I don't have anything in the denominator or fraction, and then I can solve for it easier. So it's going to be V1 times T2 equals V2 times T1. So it makes it easier to solve. Then I want to solve for T2. So T2, I want to get by itself. What do I need to do after I cross multiply? What do I need to do with T2? Or I'm sorry, V1. So I got to get T2 by itself. So what do I need to do to both sides of the equation in which to get it? Divide by V1, right. So divide both sides by V1, and I can plug my numbers in. Now if you notice, I didn't put numbers in until I solved for my variable. I think that's a good way to do this other than just moving your numbers around. If I can move symbols around, that's easier. Less writing. So now I'm going to take V2, which is 325 milliliters, and T1, 290. Now, what happens, I'll have students that don't write it out, and they'll put the wrong values. They'll put the volume there at the top would be 130, and so If you have something to look off that you can just transfer the numbers into that symbol, it's easier. So 293 Kelvin divided by my V1, which is 130. Milliliters cancel out. I end up with Kelvin as my answer. So we know that the temperature has to go up. So we know it's going to be above 293 Kelvin. It is 732 or 733 Kelvin. Well, let's say that the whoever has this thought, they want it in Celsius, they don't want it in Kelvin. So with 733 Kelvin, what would that be in Celsius? What would we have to do? Subtract 273. Okay, you can't add 273 and subtract 273 until you get, you can't, Kelvin has to be done within the equation. Okay, you got to make sure you do that. So then your answer is 460. So if they want it in Celsius, that's what you get. Any thoughts on that process? So my original equation is V1 over T1 equals V2 over T2, and then if I need to simplify it, I'll cross multiply. Okay? But my original setup to get my constants was V1 over T1 equals V2 over T2. Okay, so there is a site that's on Google Classroom that you're going to go to, and it's going to give you a choice. It's right here. And it's going to give you a choice of Boyle's Law or Charles' Law to look at. So we did Charles' Law. We'll do that one first. And then we've got a problem to solve. You got to hit new problem though. Okay, so we're going to use Charles' Law. So we got 12 liters. We got 132 degrees Celsius. And the temperature goes to 210 Kelvin. It wants to know the volume in milliliters. Okay? So let's see what we need to do. So we have 12 liters. 12 liters is V1. T1 is 132 degrees Celsius, but right away I know I'm going to change that to Kelvin. So I'm going to cross through 132 and I'll make it into Kelvin. So in Kelvin, 273 plus 132, what's that give you? What's that? Close. 405, right? So 405 Kelvin. My ending temperature, T2, is 210 Kelvin. It's wanting what's the volume in milliliters. I got a problem with milliliters and liters, so we can either convert before or afterwards. Let's convert before. So the 12 liters, how many milliliters is that?
12,000.
12,000. There's 1,000 milliliters in a liter. So there's 12,000 milliliters. So now I can set it up. So I'm going to go V1 over T1 equals V2 over T2. Cross multiply. So now it is V1 times T2 equals V2 times T1. From there, go ahead and solve the problem and see if you can figure it out. Plug in your numbers. Or I guess at this point, just solve for your V2 by switching your symbols around, and then you can plug in your numbers. So go ahead and do that and see what you come up with. So Boyle's law says if we keep temperature with not changing, and we keep how much gas we have constant, where it doesn't change, then the two of them will change in opposite directions. They say that they're inversely related. So we're going to do an experiment with a syringe. And our starting volume is going to be 20. We're going to start at 20 milliliters. And then we're going to go up to 40. So we're going to extend it up to 40 and hold it there. If we let go, it'll go back down to 20. Okay? So we'll take it out. It's going to go back. So because we know the pressure inside is less than the pressure outside, and because the outside pressure pushes it back to the original pressure. Okay? So we're going to do a problem with this. It says pressure is inversely proportional to the volume if you keep the temperature and the amount of gas constant. If you take pressure times volume, you get constants that are consistently the same throughout the experiment. Okay. So what we're going to do, we'll set up our equation, and it'll be P1 times V1 equals P2 times V2. So we're going to put our P1, V1, P2, V2 down. So the pressure inside this tube is the same as the air pressure in the room, and it is 718 in here today. So 718 millimeters of mercury. The volume, we're going to start out at 20. We're going to take the volume out to 40. Now let's go to 45. So we're going to take the volume out to 45. What's the pressure inside here right now? Well, if we had a pressure probe, we could hook it up, but I don't. And I want to know what the pressure is in here of this gas under those conditions. So solve for P2. See if you can solve for P2. Are units okay? Milliliters are the same. They'll cancel. I'll get my pressure in millimeters of mercury. So go through and solve for pressure. P2. So P1 times V1 equals P2 times V2. Divide both sides by V2. Plug my numbers in. Milliliters cancel. 319 millimeters of mercury. Okay, let's say that, you know what, I don't want millimeters of mercury. It asks for atmospheres of pressure. So, what do I need to do to get it in atmospheres of pressure? So I want atmospheres. I want ATMs. What would I have to do to get it to ATM? So I got 319 millimeters of mercury. I've got to get it to ATM. So I got to convert millimeters of mercury to ATM. So, yes? 760 to 1, right? And then we just divide it out, and it gives us an atmosphere. So sometimes, just be conscious of what they're asking units and what they're going to be. Just like the milliliters and liters. So if they're asking for atmospheres, and you get an answer in millimeters of mercury, then you'll have to convert it, and that would be 0.42 atmospheres. If you had to do that. Okay? Make sense? That takes you to both types of problems. And I'd like you to work on those for tomorrow. Do a few of them. Okay? So Boyle's Law and Charles' Law. Work for a few of those. We'll probably have a bell ringer tomorrow. If you don't get any right on the bell ringer, then I know you probably didn't practice. And then I'm going to have you practice so that you can get credit for doing the assignment. Okay? If you do well on the bell ringer, I'm assuming that you did the problems. I don't know or not, but if you don't do well, then you'll probably get an assignment where you'll have to do some of these. So look those up, do a couple of them for tomorrow, see if you're getting them right, then you'll be fine on the bell ringer. I will always give you, the formulas. On all the gas laws, I give the formulas, so you don't have to memorize those. Okay? Right. So the lab is due tomorrow. You want to work through some problems. I'll know if you get on or not. At least get on, because you'll be on Google Classroom and it'll say that you have done it. Okay? I got on, so.